Let's talk about limits and derivatives of logarithmic functions. At the top of the page here, you can see the two basic graph types for logarithm graphs. So if you have y equals log base whatever of x, there's two different general shapes that graph could take, and it all depends on the value of the base of the logarithm b. So we know that number, because it's also like the inverse function would be b to the x, it has the same rules as that number, so it has to be positive. And it matters whether it's greater than 1 or less than 1. So this is the same division between graph types that regular exponentials had, b to the x. All right, so for logarithms, if that number b is greater than 1, then it's roughly going to have this graph shape here. So the far right end of the graph kind of slowly goes up and up forever. And then the left end of the graph, our domain is all positive numbers. So we're not going to go past the y-axis here, but we do have a vertical asymptote here on the right side of x equals 0. If b is a number less than 1, so this will be like a decimal or a fraction between 0 and 1, it's that same picture just flipped upside down. So it would have this general end behavior. So now the far right end of the graph goes down very slowly. And then the left end of the graph, we still have a vertical asymptote on the right side of x equals 0, but now it's headed up on that asymptote instead of down. All right, so these general graph shapes are enough for us to pull off a great deal of limits that involve logarithms. So that's what we'll talk about in these next few examples. All right, so the first two examples here are limits that involve the function ln of x. So off to the side here, I'm going to think about what that graph looks like. All right, so ln of x is log base e, and e is about 2.7. So it falls into this graph type here. So if I need a quick sketch of y equals ln of x, I know it roughly does that. All right, the first limit I'm being asked is x approaching infinity of this graph. So I'm going to look at the very far right end behavior of this graph. That's kind of going up and up this way. That keeps going up forever. So my answer for this limit will be positive infinity. The next limit here, we're not going to see a logarithm with a limit going to negative infinity anymore because there is no far left end of the graph, right? We just kind of stop at this vertical asymptote. So the kind of next best thing to ask is what you see here. The limit as x approaches 0 from the right side. So back to the same graph of ln of x. As I plug in x values very close to 0, their y values are increasingly large magnitude negative numbers. So this graph is headed down into the vertical asymptote. So this limit will be negative infinity to reflect that graph is going down on the right side of x equals 0. We'll have very similar thinking for the next two. So both of these are log base 1/3. Because 1/3 is less than 1, it's going to be this other graph type where it goes decreasing from left to right. So y equals log base 1/3 of x. Just a quick sketch is going to do that. All right, so the first one is asking as x approaches positive infinity. So again, we're going to look at the far right end behavior of this graph. This is headed down and out forever here. So I'm going to say the graph is headed down. So this limit is negative infinity. And then finally, again, we have the limit as x approaches 0 from the right. So we're looking at plugging in x values very, very close to 0, like x equals 0.1, 0.01. And we're tracking their y values. And those are just getting bigger and bigger and bigger up to infinity because of that asymptote. So we want to say this graph is headed upwards as you approach 0. So this answer will be positive infinity. All right, with the rest of this video, we're going to talk about derivatives of logarithm functions. And we have our two big derivative rules right here. All right, so somebody spent some time figuring out how the limit definition would work out with a logarithm in it. ln of x is very special. So the natural log, this is the log with base e, its derivative is 1/x, which is quite nice. All the rest of them will use this rule over here. And just like for exponentials, This rule does also include ln, it just simplifies down to 1 over x, so we very often just think of it as its own rule, so that we skip the simplifying step and just go straight to 1 over x. Okay, so this rule says if you have the derivative of log base b of x, it'll come out to 1 over x times the natural log. So this log right here is always ln. It doesn't match that log base there. So it's always natural log of b, which was the base of the original log. And again, notice if we originally started with ln, that would be log base e. So the b is e. We would have 1 over x ln of e. And just like in the e to the x derivative, ln of e is 1. So this simplifies down to this 1 over x that we use. Okay, let's see these derivative rules in action. I have 3 examples for us to go through in this video. The first example here, we have some constant multiples out front, the 3, the 5, and the 7. But otherwise, because there's addition between the expressions, it's just 3 separate derivative rules that are going to use what we just established in that. Okay, so the derivative of 3 times the ln of x is going to be 3 times ln of x's derivative, which we now know is 1 over x. So I would leave this 3 times 1 over x, but you could certainly simplify it to 3 over x if you wanted to. The next one will have 5 times the derivative of log base 2 of x. We'll go over here and say, okay, if the base is 2, like I have here, its derivative will be 1 over x natural log of 2. 1 over x natural log of 2. And then we'll use the same rule for the next one, but instead of 2, it's a 9. So I have 1 over x ln of 9 instead. All right, so let's see these logarithm rules kind of wrapped up in more complicated derivative situations. This first one, we have ln of x squared plus 3x. Because x squared plus 3x is in the ln's parentheses, this is composition. This is f of g of x. So my derivative will call for the chain rule. The outer function f is ln of x. The inner function g is x squared plus 3x. Okay, so if I plugged all this in for x right here, I would have my original function ln of that stuff. Each of these derivatives for the scratch work are one step. This f prime uses our new derivative rule for ln of x. And then we put it all together in the chain rule formula. So f prime of g times g prime. F prime of g times g prime. And because g prime has addition in it, this is mandatory parentheses. 2x plus 3 in parentheses. Or if you wanted, you could make this the numerator of that fraction. But I'm going to leave my answer in that form. All right, let's try one more that also has a lot going on. So here we have log base 4 of some stuff. So this is composition again. So I'm going to start off identifying this calls for the chain rule. The outer function f is log base 4 of x. And the inner function g is the x squared e to the x, right? So if I plugged this into this function, I would have my formula. F prime is going to be our new logarithm derivative rule with a 4 in for b, so 1 over x ln of 4. And then for g prime, we stop and say, oh, well, this isn't just one derivative rule. This is multiplication, right? X squared times e to the x. So this on its own will be a little product rule on the side. X squared and e to the x are the pieces. Their derivatives are 2x and e to the x respectively. All right, so I'll product rule this stuff, f prime g plus g prime f, to get this last piece of my scratch work. So I have f prime g plus g prime f. All right, now I have all 4 pieces for my original chain rule. So I'll put together my final answer. Using the blue, f prime of g. So when I plug in x squared e to the x in this f prime formula, it goes in for the x right here. So I'm going to have 1 over whatever ln of 4. So f prime of g. Because there's no addition or subtraction here, I don't have to have parentheses around x squared and e to the x getting plugged in, but it's definitely not wrong if they're there. This is f prime of g, and then times g prime is times all of this, and this does have addition, so I've got a mandatory set of parentheses on it. 2x e to the x plus e to the x squared. And just like in the last example, if you wanted to, this whole thing in parentheses right here, you could also write as the numerator of this fraction, but it's not necessary. This is a perfectly good place to stop.